So yesterday I proposed two options. Either I do an overview on the two main scenarios for addressing the Higgs mass problem, the standard model, supersymmetry and compositeness. I'll give an overview. Then discussing with some of you, I realized that probably doing one of them, the one that is, in a sense, easier to express, to present in one lecture, that is to say compositeness, would probably be the better solution. In case anyone is interested, I can also devote in the next week or the week after the next one discussion on supersymmetry. Okay, that's not an issue. But before going, let me tell you this. So the net synthesis of yesterday's discussion is that when you look at the standard model, there are two extreme limits in which you can regard this theory. The first limit is the one where the standard, of course you have, the idea is that the standard model should always be viewed as an effective theory with a certain physical cutoff scale, and this physical cutoff scale, like in all physical situation we have been familiar with from the beginning, controls the expansion in the structure that manifests itself through a set of higher dimensional, higher derivative, higher field power operators, okay? And in the standard model, if you take these scales that control the expansion to be very, very large, you understand basically automatically several properties of physical reality, starting from baryon number, lightest of neutrino masses, individual lepton numbers, conservation, the peculiarities of the G mechanism that are responsible for the very special G mechanism that is responsible for the very high suppression of flavor and CP violation in the standard model, which goes hand in hand, in fact, with very high precision with what we observe in experiments. Okay, so this turns out that these features appear to be very delicate, because as soon as you consider the next stage in the tower of operators, dimension 5, dimension 6, they're all gone. Okay, they're all gone unless those couplings satisfy some specific, very precise correlations with the couplings of dimension 4. In other words, that the sources of flavor violation are aligned with those at dimension 4, that for some reason baryon number is not violated, and for some reason lepton number is violated by such a tiny amount that neutrinos turn out to be light. Okay, all stuff like that. So there are these two limits, and you could consider these two limits as the first, the limit that satisfies simplicity. Okay, it's very simple. The things that you don't see disappear. On the other hand, as we argued, the separation of scale that corresponds to this situation in the standard model, with the presence of an elementary Higgs, doesn't seem natural. Conversely, the other situation, in principle, is natural, because you don't have any big separation of scales. So it may be unnatural for other reason, but it's not starkly unnatural. But on the other hand, it looks like the automaticity of the standard model, the simplicity of the standard model, the effortless, the amount of effort the standard model makes to adapt to the data, flavor, lepton number, and all that, here requires a very clever correlation of parameters. So it's not simple. Ideally, this suggests a question. Ideally, we would like to have a world where both naturalness and simplicity are realized. That is to say, a theory that replaces the standard model right at the weak scale. So where the problem of the origin of the big separation of scale between the weak scale and the next layer, okay, is resolved maybe because, maybe by one of the two mechanisms for natural hierarchies I discussed yesterday, yes, marginality or symmetry, by one of the two. And yet, even though this theory is not the standard model, it has more stuff in it, it has different stuff in it, yet it shares the same properties in terms of symmetries, flavor, variant number, lepton number. All the magic of the standard model is preserved in this natural theory. Okay? So then the question, or the BSM question is, can this be realized? Okay, and the story of BSM of the last few decades, if you want, is just the story of the effort to realize that. And the very fact that I use the word effort just tells you that this is not automatic, like in the standard model. In other words, that the field itself is defined by the fact that realizing this ideal is not easy. Okay? And that's, in a sense, it's already implied by our operator analysis, right? The operator analysis seems to suggest that all these results here are very special by the fact that we decouple operator. As soon as you have, bringing down the cutoff represents the generic theory. So we already know that generically this is going to be different. So that means that this idea must be a special. Yeah.
So you went to.
But of course you have to. But this is maybe you're missing something. Maybe there is this idea. Yes. Go ahead.
So it took you a while to define in the last few days what you mean by naturalness and how precisely you can assess whether something is natural or not. So is there an analogous criterion for what you call simplicity, or is it another?
No, okay. Simplicity, I mean here, what happens in standard model, that the things that you don't, you may say the things that you don't want are associated, for instance, to irrelevant operators. So you don't have to make additional assumptions on the structure of the couplings. Well, for instance, if one example as concerns flavor, you're raising a good question, because let me do the following. Imagine now, I've seen this, in fact, basically this is mostly where we end up with in BSM. So you see the standard model at the normalizable level has only 3 sources of flavor violation, the Yukawa couplings. And you can assign these Yukawa couplings transformation properties under this putative flavor symmetries of the kinetic theory. And it turns out, as I tried to imply, I mean, I didn't go into detail, that it is this, I don't know how to say it in English, paucity. In fact, there are very few sources, and the sources are limited to this, okay, with these specific quantum numbers, given their value that are measured, because their value are fixed by the CKM mixing angles and by the eigenvalues, the fermion masses. Given the observed values of the Yukawas, and given the selection rules, the effects violate flavor recipe, particular flavor change in neutral current, meson, anti-meson mixing, they're all very suppressed. Okay? On the other hand, if I write a dimension 6 operator with 4 fermions generically, this gives much bigger effects. However, those dimension 6 operators with 4 fermion legs, if you look at them in flavor space, they are tensors with 4 flavor indices. So you could imagine that the couplings that fill those indices are specific combination of the same Yukawa couplings, okay, constructed with the Yukawa couplings to match precisely that. Okay? So in a sense, this would be natural. This would tell you that the Yukawa couplings are the only source of flavor. This is a fundamental theory which in some way, even above here, or here, okay, even there was perhaps a previous stage of evolution above this scale can be some new physics, where there was exactly the same property as in the model, that the Yukawa coupling were the only source. Of course, the best explanation for that is that the Yukawa couplings are the only relevant operators with flavor quantum numbers, okay? So that could happen, okay? And that, in a sense, it would be natural, but it requires a very special. Now, constructing a theory where the Yukawa couplings are the only relevant deformation above the width scale, that's not true. And
maybe.
Or you can make assumptions that they are the only sources above the weak scale and requires specific construction to be realized.
But maybe to ask this question a little bit differently, what would be an example? Let's say we have a theory which has the same meta content as the standard model, but but there would be something which doesn't work, so that would require some very special choice of parameters, right? What would you call it non-simple? Can you give an example like this?
Simplicity, naturalness of the UV completions allowed?
But you see what I'm trying to ask. I'm just trying to...
To me, simplicity, in this sense, simplicity is the... simplicity here is the amount of assumptions, model building assumptions that I have to make to concoct a situation where this is the only source. Well, in the standard model, I don't have to make any assumptions. Okay, this comes just from the field content. If you want, that's the...
No, but that's why I'm trying to ask my question. So let's say field content was the same. Is there a way to spoil?
You mean the field content was the same?
Is there a way to spoil standard model without changing field content but make it non-simple? Because it sounds a little bit circular, right? Because standard model was constructed to reproduce data. And it's quite convoluted, right? The Yukawa structures, they have the Yukawa constants, right?
I'm not objecting
there.
to the, I mean, the Yukawa couplings themselves are, there's some complexity there.
Right.
But I'm not calling that complexity. To me, the simplicity here is the effort you have to make. See, when you try to make...
No, but that's why I'm trying to ask my question. Could it be...
So for instance, if you had models with flavor symmetries, you try to construct a situation where a flavor symmetry protects these things, then you normally end up with more. Of course, you're trying to explain more things. Then, of course, it requires more assumptions. I think it will become more clear as we show an example, right? What this means. But simplicity here, in the sense of the model, is rid of the fact that you have a very minimal set of relevant or marginal operations. So this is the way I call it. The same property is not satisfied anywhere else. So you don't have the same. So in the standard model, the relevant operators are the things we see. Okay, that's not the case in
the relevant operators are fixed by.
The relevant operators are the quantities we observe, and they are precisely the structure such that...
Relevant, you mean not relevant, but relevant.
Marginal. I mean, relevant in the sense dimension equal than 4.
Right.
Okay.
The what? It doesn't hear what.
In the standard model, the operators, so the effects, there's a one-to-one match between what we observe and the operator's dimension less than 4. Besides data. In the other cases, this match does not exist. There's either more stuff, for the supersymmetry there are more operators you can write down, while in compositeness, and now we're getting back to the stuff, but you see, but now the lecture is totally disrupted.
Yeah, sorry.
What's this guy? I mean, you want to get to the, okay, in the case of compositeness, some of the things we observe are in the same class as the things that we don't observe because they are irrelevant. And because of that, then we have to introduce extra dynamical assumptions to match what we see, right? We need to select among effects that come at the same order, can come at the same level, and this requires additional dynamical assumptions.
Well, which is a little bit like the structure we have in Yukawas. Like, for instance, if in standard model all Yukawas were order 1, that would be even simpler theory than what we have, right? So, just don't.
I wouldn't say that is a simpler theory. So
well, but it's kind of here. You need to put sub coefficient 1 and some like 10 to minus 3, right? 10 to minus 5 to explain data. So what I already say that okay, we need to suppress some of the marginal operators. Compared to a theory
no, but let me put it this way. In the standard model, there are there are few. There is only one source that has flavor quantum number. In the other, there are more. Okay, so in terms of the global symmetry of the kinetic term, I don't know. Look. Look, Sergey, I don't know. Maybe this is vague. I don't know. I understand. So take supersymmetry. Okay, supersymmetry. You take it. You add the soft terms, and they are all. If I just play, they're all like in the standard model. They have to be very specific. So you're saying, oh, but that's also in the more. They have to be more. I mean, if you try to make a theory of flavor, it's easy to make a theory of flavor it's easy in supersymmetry to make a theory of flavor that explains the Yukawa and the soft terms. And this theory, in order for the soft terms to be as clever as the Yukawa, have to be very special. You see what I'm saying? It's easy to make a theory of flavor for just the Yukawas. It's easy. Making a theory for the Yukawas and for the soft terms is harder. It requires more assumptions. Anyway, I don't know. Look, this is taking time.
No, go ahead.
So there are these two, the two main scenarios that try to address that are compositeness and supersymmetry. Okay, if you want, compositeness realizes a natural hierarchy by the principle, by the mechanism of marginality I was discussing yesterday. In other words, the theory that replaces the standard model above the weak scale does not possess an operator like the Higgs mass. Okay? It doesn't possess operators of dimension strictly less than 4. Well, in the case of supersymmetry, the theory does possess scalars. In fact, it possesses plenty of scalars. However, there exists a symmetry which makes those masses, the fact that which makes the possibility of having those masses small natural. It doesn't yet explain why those masses are small, the symmetry per se, but it sets the stage for an explanation. And in fact, we even have the explanation in the case of supersymmetry of why those masses are small. Okay? That is because of the specialty of supersymmetry. Supersymmetry has a special property called non-renormalization theorem, which dictates the way masses, okay, terms that look like masses that are the coefficient of superpotential are generated. And this theorem dictates that these terms are generated by non-perturbative effects under broad conditions, okay? And if the theory is weakly coupled, non-perturbative effect generates small masses. In the end, these non-perturbative effects make this generation of mass very similar to marginality, okay? But anyway, okay. So these are the two scenarios. Now, discussing, now I should say that these ideas were proposed, compositics per se as a broad idea was proposed in the late 70s. When it was realized, this problem of when the unnaturalness of the scale separation was realized, this was the first thing to be proposed. Supersymmetry was being developed formally at around the same time, perhaps even a bit earlier, but roughly at the same time it was realized that it was relevant for the question at hand. And it should be said that right at the start, and for quite a while, and maybe even now in a sense, supersymmetry seemed, and perhaps in the same, is the most convincing scenario. In a sense, this is because supersymmetry is closer than compositics to really the standard model. In other words, the bare bone structure of supersymmetry is the same as the standard model. You simply double the degrees of freedom in the standard model by the superpartners. But at the end, it's structurally closer to the standard model. But the structural closeness also implies that there must exist states that are just replicas of the ones we have seen, the electron, the W. There's a replica for each of the states we have seen. And And the very fact that these replicas want to have properties similar to their standard model partners, the natural expectation for supersymmetry was that supersymmetry states show up at very low energy. In fact, in principle, in a sense, supersymmetry, the appearance of supersymmetry in colliders, in experiments, was already in a sense laid 25 years ago at lab. Okay, so the natural scale of supersymmetry is below 100 GeV, and of course, then you can make it less simple, as I was saying, and come up with additional clever mechanism and push it up a little bit. You can have clever mechanisms that make sure that there is no flavor violation. Perhaps you can say that these mechanisms are not so clever. Okay, they are. It's up to you to judge. I mean, perhaps we should not be so restrictive. So, as time went by and data accumulated, supersymmetry acquired more and more difficulty, okay, compared to what it was in the beginning. In fact, compositeness started not very well, okay, and it started not very well for essentially two reasons. One that I will illustrate, and the other main reason is that it's very hard to construct models with strong dynamics because we cannot master strong dynamics, okay, easily, and it's even difficult to explore models with strong dynamics. Weakly coupled models, you write the Lagrangian, you go on and do computations. But strongly coupled dynamics, how do you proceed? It's not clear, okay? We don't have the tools. And there were intrinsic phenomenological difficulties. A sort of breakthrough came in the late 90s with the discovery of warp compactifications, which through holography, these are just five-dimensional models in a slice of anti-de Sitter, which, even though they are extra-dimensional models, if you look at them in a certain perspective, they are truly four-dimensional theories. Four-dimensional theories that are valid up to a very high scale, in principle up to the Planck scale. And in this interpretation, I mean, in this way of looking at them, they are equivalent to models where some of the particles are composite. And in particular, you can construct such theories in such a way that just the Higgs sector is composite. Okay? And this has spurred, has allowed our community to construct more realistic examples of composite Higgs. Okay? More realistic than we could have before. And now, the fact that these examples are more realistic, and the fact that for these models, it is more expected that the particles are heavy, okay, than in supersymmetry. In fact, right away in the very first version of composite Higgs, everything was heavy, even the Higgs, 2 TeV. So that of course it ruled out, okay, and of course discovered the Higgs requires that the Higgs particle should exist. But that is compatible with compositeness, okay? And I will explain in a sense why. So as I said, as time went by, this scenario acquired a little bit of more dignity with respect to supersymmetry, okay? And this is why it's now also studied. Of course, with the LHC, already labeled to some extent, but LHC has also put stronger constraints on this. Okay, so now it's a question of. I mean, I don't want to get into the question what is worse or what is best. Okay. It remains true that even at this stage, the composite scenario requires more seemingly ad hoc assumption to be alive than supersymmetry. Okay? And this is what I call the lack of simplicity compared to the standard model, but perhaps I should use another word. Okay? not automaticity. I don't know how to, maybe this is not the right expression. I think it's more clear to see it when you try to do it than that. Okay. So now I should say also that one of the features that for a while and still now makes supersymmetry more attractive than compositeness is that supersymmetry pushes is nicely compatible with gauge coupling unification. This is something I must say. Already in the standard model, there is an interesting fact which cannot be put aside. I think it's important. If you look at the couplings, the 3 gauge couplings, the SU3, SU2, and U1 at around the weak scale, these couplings are comparable at that scale. Okay? And as you know, these couplings evolve logarithmically, so they evolve very slowly. Okay? And then you can ask yourself, just close your eyes, even forget lambda QCD. Let's say you're given the couplings at the weak scale, and now extrapolate them, and they evolve logarithmically very slowly. Is there a point is there an energy where, for some reason, these couplings become comparable or equal with some suitable normalization, which theoretically you can think what it should be? Okay, I don't want to get into that, but is this the case? And given that they evolve logarithmically, you know, when you have a log, it could be that the scale where maybe this happens, this unification, but it may happen at 10 to the minus 80 GeV. Okay, of course, it doesn't happen because the coupling becomes strong before, but it could happen at a very low scale, 10 to the minus, or it could happen at 10 to the 100 GeV, okay, or at 10 to the 1000 GeV. Instead, what happens is that these couplings tend to get close to one another within, say, 20%, okay, at around 10 to the 14, 10 to the 16 GeV, which is to say, at a few orders of magnitude below the ultimate scale of physics, which is the Planck scale. So that's very interesting. They get comparable around, not far from the point where also gravity becomes important. So there may be the possibility that all the forces become comparable.
And also close to the scale which we used before, the neutrino mass, for instance, right? So that's also from lambda UV, which we
Sure, I'm about to say. So yeah, and this scale is also not far from the scale that is suggested by neutrino masses, if you assume that the couplings that enter the neutrino for field operator two leptons and two scalars is of the order of 1. Of course, if you take the coupling smaller, which you could take, then the scale should be lower than 10 to the 14. 10 to the 14 is the scale with coupling for order 1. Okay? But anyway, grossly we know. Look at the standard model, there is 5 orders of. When you say that there is something happening at some scale, look at the standard model. Between the electron and the top, it's 5 orders of magnitude. So there is a. Anyway, it could be. It seems like in the right ballpark. It's interesting and enticing because the theories that entail unification of coupling, like SU5, imply proton decay. And we have seen that the present bound of proton decay, experimental, is again around that scale, 10 to the 16. So if this idea of unification is really correct, there may even be a chance that we discover proton has a lifetime within our lifetime. So that's certainly exciting. What made supersymmetry also more exciting is that if you add, so while in the standard model, this unification is not perfect, it works within 20–30%, which means that to see in a realistic unified theory, there should be additional matter around the scale that fixes this unification. While this is not, this is imaginable, what is remarkable about supersymmetry is that this is not needed. Is that the spectrum of, when you add supersymmetry, the spectrum of the supersymmetric theory is such that the unification works basically within a few percent. Okay, so in other words, the coupling. And that makes it even more consistent with the natural expectation for threshold corrections at the unification scale. So it works very nicely. And this is what had prompted many of us to be very And the other thing is that supersymmetry is something very different than what we have seen so far. And the way, if you want, Nima says it, compositics or anything like that is yet another example of superconductivity or stuff like that, where you have some Higgs play the role of the field that breaks the symmetry, being some composite made of other fields, particular fermion, anti-fermion, like you have in QCD, like you have in superconductivity. I don't like having the universe to be a new type of metal. I don't know whether to go like that. I think even in that other case, there could be, as I will show you, there is the possibility for stepping in on new ground as concerns phenomena in quantum field theory, even in that case. Okay. So let me therefore now spend time in illustrating broadly the idea of compositics. And I have here 5 or 6 transparencies on supersymmetry. Maybe if time permits, I will go back to them. Okay, let me stop share. Let me control. Here, I should not erase this. Okay, so what is the idea here? Okay, so in the standard model, you have a scalar field, you have an elementary scalar field, the Higgs, which has dimension 1. What does it mean it has dimension 1? It means that its 2-point function, let me be very schematic, at very short distance goes like 1 over x squared, okay? The fact that this particle is, and the fact that, okay, so this, when this happens, we say that h is dimension 1, okay? Now, along with that, the fact that the Higgs is a weakly coupled particle also implies that if you do the same thing for the product of 2 Higgses, okay, and you compute the same thing, and you look diagrammatically, this is you're exchanging 2 legs, 2 lines between x to 0. If the theory, if there were no interactions, this would go like 1 over x to the 4th, because you're simply squaring 1 over x squared, which is 1 over x to the 4th. And this is interpreted with the fact that this object here, h, dagger h, has dimension 2. Okay, so it is what we call an operator, a relevant operator. So you can use its dimension sets in an effective theory the dimension of the coefficient that with which this can appear in the Lagrangian. Okay, and this tells you that you have something like h, and lambda is large. This is a very large coefficient, and everything gets added. And the fact that the Higgs is weakly coupled tells you that this picture doesn't change dramatically, okay? If you add interactions here, up to logarithmic effect is still true, okay? So, in a sense, the dimension of a field is like the energy or the mass of a particle, okay? And when particles are not interacting, if you take two of them, their energy add up, okay? And there's little potential energy. And so it's just the sum of the two, okay? So when the fields are free, they don't interact, the dimension of taking product of the fields just add up, okay? And interactions change this picture. So it's very similar to that. Okay? So the idea of a composite X is one where, if you want, the analog of H dagger H, okay, where H is a composite and is made of very interacting okay, it's composed of strongly interacting fields, okay, and which means that when you compute its two-point function, you should view it like HH. You should view it like as if you had more than one field being exchanged, and these fields interact very strongly. And now, if you play the same game, and now you have you have H and H dagger H, so you have so this is X and 0. If you now take the propagator of the composite field, taking two powers of the X, remember, this X, it's a self-already composite, okay? And then again, you have, they go like this, but they also exchange between them, okay? There's also, so it means that if two particles are made of very strongly interacting stuff, if you add them, they also interact a lot, okay? And therefore their energy is not additive. And the very same way here, the dimension is not additive. So what you have is that the dimension of H dagger H is different than twice the dimension of H, okay? It's not additive. And in particular, yeah, it can be bigger, okay? So, so that's the idea. And the idea is that the dimension of the idea is to be in a situation where the dimension of H dagger H is either slightly less than 4 or of order 4 or larger, okay? In which case, the relevant operator that you would need in any case to generate a scale is not given by this, but is given by something else. Okay? So the basic idea is this, okay? To have let's see whether I remember, but I'm forgetting something that I need to say. Okay, so the concrete example of this idea is given by the Technicolor. Okay, Technicolor is a model where I already mentioned essentially yesterday, where in addition to SU2, let's forget for a moment ordinary color, and let's just focus on electroequivalent numbers. Okay. So where in addition to SU2 cross U1 hypercharge, you have a Technicolor gauge group. And it is the Technicolor gauge group, GTC, becomes of order 1, of order 4 pi, at around the TV, at order T. Okay? So it's a sort of replica of QCD, but with a scale that rather be 1 GeV is a factor of 1,000, or maybe 10,000 larger, okay? And so the idea is that this theory has quarks, which are called techniquarks, in vector-like representation of SUN, but in principle in chiral, it depends on the models, representations of SU2, they don't need to be chiral, they may or may not, but so for instance, you can have T to be A is the Technicolor index, and alpha is the SU2 index, okay? So this is a fundamental of SUN, doublet of SU2. You can also have technifermions, there are also technifermions that are singlets of SU2, okay? With suitable quantum numbers, okay, under U1. And the idea here is that there exist bilinears, like of the type T bar alpha TA, okay? So these are fermion bilinears which have the same quantum number as the Higgs, okay? Which play the role, which have precisely the quantum number of the Higgs, okay? And then what happens, the idea is that what happens is very much what happens in QCD. The strong dynamics gives rise to an expectation value for this bilinear, okay? Breaking the chiral symmetry of this gauge theory, but the chiral symmetry of this gauge theory is nothing but the gauge symmetry. I mean, it contains the gauge symmetry, the standard model gauge symmetry. So this expectation value spontaneously breaks. If it's 0, breaks, like in the standard model, breaks SU2 cross U1 down to the charge. So you realize precisely the breaking that you have in the standard model. This breaking gives rise to, you're breaking 3, I mean, there's an addition, but ideally you break 3 generators, you generate 3 Goldstone bosons. The Goldstone bosons are written by the WZ acquire a mass, and that's the same story as in the standard model. The only thing is that in this situation, the analog of the 4th component of the Higgs doublet that you have in the standard model, which remains like a light scalar particle, here it's a composite, or in fact, it's a very broad resonance, and its mass, see, the point is that this theory is strongly coupled. So the typical coupling of this theory is G star is of order 4 pi, okay? It's large. At this scale, the coupling, the technical coupling, sorry, is large, okay? And as you know, as you're familiar in the standard model, how do the mass of particles scale as a function of their coupling to the Higgs and the web of the Higgs? Remember, all masses go like a coupling times the Higgs web, which is V, okay? So, be a Yukawa, a gauge coupling. Masses are always a coupling times a web. In fact, you can even invent a symmetry that tells you that it has to be like that, okay? There's some, you can put back units where h bar is not one that has dimension. This is actually fixed by a selection rule. So here, therefore, what you expect for the mass of the corresponding resonance, when it's a strongly coupled theory, so the coupling is of order 4 pi, so we'd expect the mass of the resonances, in particular of the, let me call it Higgs with quotation, okay, because this is going to be eventually a broad resonance. This is of order 4 pi V Fermi, okay, so which is about 2 TeV. Okay, so we would expect to have some very broad resonance because a strongly coupled decays very fast at around the scale. It could be 1. I mean, this is very rough, right? And this is not what we see, okay? Because we see a very sharp, very narrow, light resonance is known as the Higgs boson, okay? That's the essence of the of the Higgs mechanism, is that, yeah, if you are in a situation like this, okay, where there's no Higgs boson, so what is the deal? The deal is that without the Higgs boson at this scale, the interactions of the longitudinal vector boson, the Eaton one, okay, see, in this situation, the longitudinal vector bosons are part of a strongly coupled sector, okay? A sector, a strongly coupled sector with a typical mass scale of a 1 or 2 TeV, okay? And therefore, when you do experiments at 1 or 2 TeV, the longitudinal component of the vector bosons manifest their strong nature, okay? And in the late 80s, early 90s, when the SSC was being planned, one of the main goals of the SSC was to study interactions of electroweak vector bosons in this energy range. This is what they needed 40 TeV to go really, because when you do proton collisions, okay, but what you really scatter are the partons, which carry less energy, and the partons are not W. You want to study the scattering of W, so you have partons, quarks that arrive, they radiate a W, and the W scatter. So it's the energy of the original proton degrades a few times before you get to really measure what you want. There's the protons, they only a fraction of the energy of the parton goes, they emit a W, and then they scatter. Okay? And studying the scattering on TV was the way to study Technicolor. Then the SSC was cancelled. Okay? And the LHC was not considered to have the energy to really do that properly. But anyway, the LHC discovered the Higgs, so it's a different story. Okay. Okay, so that was the basic idea. In this scenario, there is already, you already see where things get complicated, if you want. I don't know whether to say simple compared to the standard model, because here now what you have is that the analog of the Yukawa coupling, the standard model, you have the Yukawa coupling. There's the Higgs, there is the Q, there's the U, and there is the Higgs. Okay, and similar for the down and the leptons. Here, the role of the Higgs is played by this TT bar. Okay, and you have this. Okay. So now the Yukawa couplings before were marginal, dim equal 4. Okay, this coupling was dimensionless. And now this coupling here is some y divided by some scale square. So this dimension minus 2. So it's now an irrelevant coupling. It's now one of the couplings that if the scale is high, they're hard to see. And see, in the standard model there was this, and then there was this other crap that in principle, unless it was cleverly aligned with these Yukawas, okay, which requires some specific additional dynamics to realize it requires additional structural hypotheses to have this aligned with that. And this was, of course, dimension 6. Now, in this theory, and this thing we don't see, in the standard model generically, this would screw up in a significant way what we observe in the flavor sector, unless this is cleverly chosen. Here, the screwer, the guy that screws up everything, comes at the same order as what we would like to keep. Okay, so in Technicolor, what we don't see and what we see come together. And now, if you try to construct a theory that constructs this coupling, it also constructs those. Okay? And that is making everything very complicated. Okay? And then, to make it work, you have to go through a set of constructions, which is what I call not simple. I don't know, Sergei, how would you call them? You have to go through a set of ad hoc of assumptions that really seem like ad hoc. You know, maybe simple is not the right word.
No, but isn't this just another manifestation of some naturalness? Somehow that to be unnatural to have that.
Well, in other words, let me put it this way: in the standard model, okay, let me put it. Yeah, there's another way to say it. In the standard model, you're given the possibility to be agnostic as to what generates the Yukawa coupling, because you separate the scale, the fundamental scale is very high. That scale is given some Yukawa. one day you will figure out how those Yukawas are generated. It's not difficult to come up with a theory with a system, with a mechanism that gives the Yukawas within the standard model. We can go ahead, but it's a theory of flavor, okay? But it's something that happens at a very high scale. In this case, you're forced to come up with a theory of flavor at a low scale, because this scale cannot be too high, otherwise, for instance, the top mass is too small. So the top mass is large, so this scale must be pretty low, okay? And so you have to come up with a theory for this, the origin of this at a low scale, but that theory will also generate that. But this theory will have more sources of flavor violation than the Yukawa coupling, because the Yukawa coupling are just the accidental source of flavor violation that you have at low energy. There will be more sources. The source of flavor violation in this theory are not the Yukawa coupling, okay? And in order to cope with that, you have to come up with clever mechanism or additional assumptions that align.
That is because there are also high-dimensional operators. Because otherwise, one would say, okay, just like for standard model Yukawas, we see some of them are large, some of them are small. Here we do measurements, we see some of these couplings are large, some of them are small.
Yeah, but
it's important. There is at the same scale, kind of there are high-dimensional operators, and you need kind of to do this. So it's really crucial that in standard model it's achieved by marginal operators and
yes, it's
by relevant.
Yeah,
that's really key, right?
Yeah. And in all these scenarios, instead you come up with this additional, there's always a hypothesis called minimal flavor violation now, but I don't know why they call it, I really don't understand why this name was invented, okay, but I can tell you a story about that.
Sorry.
Alberto and I wrote a paper, we were using it, but it's okay.
Sorry, just so I understand the numbers, how does the scale lambda on the board here compare to the vacuum expectation value of TT?
Whenever I put a scale below, it means that there is this, let's say, what I'm thinking here is this. Oh, shit. There is some UV scale, right? Okay? Which is always the end of physics, okay? And then there is everything happening below. So there's some UV scale where there emerges the standard model plus Technicolor, okay? Technicolor becomes strong at 1 TeV, lambda TC, around 1 TeV, and that generates the masses of vector bosons like that, okay? Now, what can I say about the Lagrangian that mixes the standard model to the Technicolor fields above this? This is the leading mixing. It's only dimension 6. So the scale here is the original one, right? If I put the scale here, this coupling would be super strongly coupled. I wouldn't be knowing what I'm doing. Maybe I should have given the picture, yes.
All right, makes sense.
Is it okay?
Yeah, that's good.
It's always implied. So, now, turns out this was already realized in the 80s by David B. Kaplan, okay, Kaplan Sr., that the situation where you have a sort of Technicolor model and there is chiral symmetry break, or there is symmetry break in that sector, and the Goldstone bosons that are associated with this breaking are precisely just those that are eaten by the W and Z, it's a special one. There can be, you can think of a situation where there is a fourth Goldstone boson, there's a fourth guy in this symmetry breaking, which is a Goldstone boson of Technicolor taken per se, but which at the end of the day is precisely the Higgs boson. In other words, there's a fourth Goldstone, and it's a pseudo Goldstone, and it is the Higgs boson. So the fact that the Higgs is composite doesn't imply it necessarily to be heavy like this, okay? If you think of the pion does not have a mass equal to 4 pi lambda QCD or lambda QCD in this case, okay? But much smaller. In particular, if you remember, at least there are two contributions, one from the quark mass and the one from electromagnetism. if you want to think of the one of electromagnetic, it's closer to what will happen for the Higgs in a scenario like this. The one that is coming from delta m pi square, coming from electromagnetism, was more like G electromagnetic coupling over 16 pi square times lambda square. Okay, so so the idea is to have something similar, okay, where you have a composite object that is actually a Goldstone boson in the perturbed limit, and whose mass is only generated by the weak interactions. Okay, in that case, you have a chance to have something that looks like the ordinary case. Okay, so this is the and this incarnation of composite Higgs is started being considered already way before the discovery of the Higgs, because electroweak data, several indirect measurements were already severely pointing towards the existence of a light Higgs. Okay, the discovery of a light Higgs was not a complete surprise. Okay, theories with the heavy Higgs, like this, had difficulty to cope with data, even though you could always imagine some additional tuning to fix it. Okay.
So even in this Goldstone case, is it easy to have a narrow resonance for the Higgs, or you'd still expect it to be broad?
The Goldstone bosons they are derivatively coupled, right? So in the limit where the Goldstone exact symmetry on shell, which is at p square equals 0, they are infinitely narrow. Perturb the situation with a tiny coupling by definition of perturbation theory. This will be a narrow resonance that will move away, right? By definition, it's a perturbing. So in other words, its coupling, okay, are weak. Okay. You can ask yourself, what is the coupling induced by there's a similar quartic coupling induced for pions by the electron, and it's e to the fourth, so it's a big coupling. Yeah, anyway. But that's because in the limit where you turn off interaction, it's derivatively coupled.
Right.
So then its coupling is due to derivatives, with the four are small if the mass is small, plus weak coupling, which are. So the idea is to have certainly, so this suggests, and of course in this situation, how to reconsider the problem of the naturalness of the hierarchy. Well, in this theory, written this way, you cannot, in this particular theory, the most relevant operator in this sector is the gauge kinetic term, okay, which is very much like in the Young-Mills theory. So you are precisely in the condition of marginality. If the technicolor coupling starts not maximally strong, but say if GTC times NTC, number of technicolors over 16 pi square, is about, I don't know, 1 in 30 at energy of order and Planck, then it takes a lot of running before it becomes strong and the hierarchy is natural. Of course, you need this C, okay? But this is a modest request, if you want. It's considered to be done. Maybe you young guys can say, no, you young guys are full of shit, this is terrible. But it seems, it's unfortunate that in looking at data, you are forced to stick your neck out and make judgments like this, right? Which is not like when you do purely formal physics, where everything is black and white, okay? You have to stick your neck out and maybe look like a fool, but that's the situation. Okay, so if you do that, then then you have this, and then there's no issue. Okay. By the way, in the particular case, this is precisely like Young-Mills because of the additional gauge symmetry, you cannot write a mass for the technifermions. The technifermions mass cannot be written, so there's only that. Okay. You making the Higgs composite. Okay, is the option to get rid of this. So in the sense of the question of what H dagger H is okay, it's this product of these two triplets. At the end, the H dagger H product, there's going to be some sort of OPE. This H dagger H, the product, will contain the gluon, the technical gluon kinetic term. And the hierarchy is controlled by that. So in a sense, the Higgs mass is replaced. So what in the standard model was the most relevant operator is the Higgs mass. Now is the technical gluon, well, is the technical gluon kinetic term, okay? Which is an operator of dimension close to 4 if you started with coupling. So you may ask, well, okay, if you, given that you're spending time making the Higgs composite, does it make sense to make also perhaps the fermions of the standard model composite, okay? And the answer to this question should clearly be based on phenomenology, okay? And the phenomenology tells us the following. For instance, at E plus E minus collision at the lepton positron collider, the LEP, we have measured with very high precision the scattering of E plus E minus at energies of order 200 GeV. And yeah, we have measured about, at those energies, we have measured about, I think, like 10,000, between 10,000 and 100,000 collisions. So we have plenty of events. And at lower energy, we have more. At the Z scale, we have more. By putting all this together, at the Z scale, we have almost probably 10 million. And putting all these things together, you can put a constraint on the scale of compositeness of electrons, okay, for electrons, which is roughly 100 TeV, 50 to 100 TeV. Okay, so that's quite impressive, okay, because these are experiments we do at low energy where we have a lot of precision, okay, and if the electrons were composite, they would appear, you would expect to have in the theory couplings like this, okay, characterized by the scale of compositeness times the coupling that controls compositeness, okay? And if these objects are bound by strong force, this coupling is of order 4 pi. Of course, you could imagine, in general, this would be like this, like number of colors, okay? So maybe it's slightly weaker than that if it's the color of compositeness, but okay. But overall, generically, this is the expectation, and then you get a scale like that. Okay. So this seems very high, and if you're aiming at compositeness around the weak scale, it's better to treat the standard model fermions as elementary. The standard model fermions are charged on the vector bosons. It's hard to imagine the fermions being elementary and the vector boson being composites, so then also the vector bosons have to be elementary. And then the basic idea is that this class of models, the scenario you can think of is a scenario where you have the standard model prime, which is the standard model minus the Higgs, okay? Take all the fields of standard model, treat them as elementary, and then there is another sector, which is, I call it the CFT, which contains the Higgs. Why CFT? Well, okay, even in Technicolor is essentially a CFT, right? This is like a QCD theory. If you go above the scale where the coupling is large, it runs logarithmical, but it goes, at the beginning, it goes to 0, it becomes small rather quickly, very much like it happens in QCD when you go from 1 GeV to 100 GeV. So a few decades above the scale of 1 TeV, this theory is very weakly coupled. So this theory is very well described by a free theory with a slowly moving marginal coupling. So it's a weakly perturbed free conformal field theory. Okay? And it's a weakly free conformal field theory whose only relevant deformation, the most relevant deformation is as dimension close to 4. And this is why you have a naturally high hierarchy. You you can think of generalization of this notion, where the theory here is not just a gauge theory, it's an abstract conformal field theory, okay? It's an abstract conformal field theory which sustains a natural hierarchy. In other words, there is a UV scale here where everything starts, and there's an IR scale which is around a weak scale, okay? Now, where this scale is, the wish of naturalists was for this scale to be as low as possible, 1 or 2 TeV. And then this wish has to compare what the data tell us, okay? And the data are telling us this scale has to be a bit above that, okay? But we will get to that. So I'm presenting you how, let's say, let me say I present you for a good part of this situation 15, 20 years ago, okay? But then I will comment on how things have changed, okay? But that's the rough idea. Anyway, but they have changed by a factor of 2 or 3 maximum, okay? So instead of 1 to TeV, it has to be 4 or 5, okay? That's the essence, okay? And which is significant, by the way. I'm not cutting it down, but for the overall picture, that's the idea, okay? Let's say this scale is like the Planck scale. This is around the weak scale. And here, the idea is that in this regime, the Lagrangian is the action of the standard model prime, which is to say the Higgs without the standard model without the Higgs, which means the kinetic terms of fermions and vector bosons, and that's it, okay? Because you don't have the Higgs here, so you cannot write the Higgs potential, you cannot write the Higgs kinetic term, you cannot write the power. Okay? This is what you have, the standard model prime is this. Then you have the action of the CFT, okay? Here, the CFT, which eventually contains the Higgs sector. This action will contain some deformation, okay? Let me call it, how do I write it? Let me call it S def. So this is some relevant operator in the CFT, which will eventually give rise to the curves of this scale. Okay? The idea is that the CFT exits at some very large UV scale, and the CFT, as it exits there, either does not have strongly relevant operators, only has operators of dimension close to 4, like Technicolor, and as soon as, with this, in this situation, a tiny seed like this naturally generates a big separation of scale. Okay? It takes a very, very, very long amount of running before this coupling becomes large and you enter into the regime. Or you could have you could have a theory where, yeah, there are relevant deformations, but for some reason, but they are controlled by symmetry, they transform under a symmetry, as for some reason, something happening at higher scales has set the coefficients of these operators to be small, naturally small, because they're controlled by symmetries. In other words, the hierarchy here is natural, it is controlled by some operator. So the example of this is, for instance, as I did before, some coupling, lambda UV, the epsilon times a singlet operator of some scalar operator of dimension 4 minus epsilon. Okay? That was where epsilon is something 0.1, 0.2. And then the other thing you need, however, and that is much. So the idea is that this theory is scale invariant. Strictly speaking, if you were exactly scale invariant, there would be no particles. Scale invariant theory does not, the conformal invariant theory does not have asymptotic states, but somehow the generation of the scales give rise to physical particles, okay, particles with mass, okay, and the Higgs is one of those, okay, and the Higgs therefore is something that emerges like a bound state here, very much like the pion, okay. Here the Higgs is similar to the pion, it gives me some light bound state, some light half. I'll get to that. However, we are missing something here because we need eventually the standard model to couple here, okay? Otherwise, the standard model will not know about the Higgs, about the electric symmetry. Well, first of all, the fact that this sector contains the Higgs tells us that this sector should contain degrees of freedom that are charged under SU2 cross U1. So in other words, very much like in Technicolor, where there were degrees of freedom with SU2 charge, here there should be. So there should be some weak gauging of an SU2 cross U1 group, subgroup of whatever global symmetry this system can have. Okay, this is G. And there should also be interactions between the fermions and the sector to generate the Yukawa. This is what I would call proto-Yukawa. And the nature of this mixing is precisely what I would like to discuss in a moment. Okay? So as I said, the situation in QCD is that you have the proton, the neutron at around 1 GeV, very rough. At 770, well, 930 MeV, MEV. 770, you have the rho, and then 135, you have the piles. Okay? And let's say present it this way. In fact, if you put the mass square, it's even more dramatic. Okay, this is not in scale. So the difference here is that these are ordinary hadrons and the pions are pseudo-Goldstone bosons. Okay, and of course, if you do an experiment going up in energy, you first discover the pion, and later you discover these other guys. Now, we have to imagine something like that happens here as well, where you have the light dye, which is the Higgs, the whole Higgs doublet, which consists of H1 plus I H2, H plus I H3. The 1, 2, 3 are the Eaton Goldstones, and H eventually is the Higgs boson. This object here should emerge very much like the pion emerges as a naturally light degree of freedom, a pseudo-Goldstone boson. In other words, the degree of freedom whose mass goes to 0 in the limit where you turn off the sources of breaking of the symmetry, which in this case are the Yukawa coupling and the gauge coupling. And the situation is precisely the same. You could rewrite this in QCD. Here you have QCD, and here you have the photon that breaks the isospin, the chiral symmetry of QCD, and gives rise and contributes to the pion mass. In fact, there's also the mass, the core masses that do that, but the situation is very similar. So in other words, yeah, anyway, this is light very much like the pion is light in QCD. And then the idea is that somewhere above, let's say here 1 TeV, around here you have the resonances. Okay, and these resonances will have to be at scales that they are the analog of what you had for Technicolor or for pi. The most natural scale with respect to those is for pi di Fermi, okay, which is about 2 TeV, 1 or 2 TeV. In fact, you would need them to be the fermionic ones should be lighter than that to comply with naturalness. I'll see that in a moment. Okay, so these are the analog of the pions. And as you know, the pions, in fact, the meson octet, and also the kaons here, the meson octet is 8 Goldstone bosons associated with the breaking of SU3 across SU3, left, right, down to SU3 isospin. Okay, you break 8. You reduce your symmetry by 8 generators, so you have 8 Goldstone bosons. Here, you would like to have at least 4, maybe more, but at least 4 Goldstone bosons filling a doublet of the unbroken symmetry. You see here, you have SU3 broken down to SU3, and this is still a good symmetry, SU3 is still a good symmetry, and in fact, the mesons are in an octet, right? Remember the octets, right? This way, 2 there, okay? This is the Meson octet, is an adjoint of SU3, okay? And here you would like, so very much like here you have SU3 as a residual symmetry, and the pions in an octet. In the situation here, you would have a similar breaking G to H. Well, sorry, this H here is not, let me write it this way, this is a group H like that, such that this H contains SU2 cross U1 if you want, but SU2, and such that the Goldstone bosons, okay, the resulting Goldstone bosons fill a doublet of H. And so this is a group theory problem, okay, and there are the simplest options that realize that are SU3 broken to SU2, okay, and where you precisely have 4 Goldstone bosons, okay, and remember here you have 8 generators. Well, you
5.
no, yeah, SU3 cross U1, SU2 cross U1. So you have 4 Goldstone bosons here, and the other option, but this is actually not optimal because this coset does not happen to have the custodial symmetry I was mentioning yesterday, the symmetry which ensures that mz square over cosine square theta Weinberg over the W square is 1. This coset does not have that, and it has a significant correction to this relation. On the other hand, there is another coset, which is SO5 over SO4. Here you see precisely it has 4 Goldstone bosons, okay, you see it right away, 5 to 4. It's like breaking from a 5 of SO5 that acquires a web, and the other 4 directions are precisely Goldstone bosons. And this is custodially symmetric. In fact, this is the simplest option that gives you the most realistic phenomenology. And this is the one that is most studied. So the idea is that, and then there are more, right? You can imagine, for instance, SO6 to SO5. This would have, so this is 4. So the Goldstones are, here there is a 2, here there is a 2, and here there is a 2 plus a singlet. Okay, there are 5 Goldstones. This is slightly more complicated, but this also has some interest. Okay, scenarios like this can be interesting for baryogenesis at the weak scale, for instance.
Sorry, and that SO4 is precisely the custodial SO4?
Yes, exactly. That's precisely the custodial SO4. Right. Well, if you want, I can do it. Yeah, I can do it. That's okay. Can we take a little break now? It makes sense to take 5 minutes.
So the 150 TeV limit, I just pulled up the PDG.
The 150
for compositeness.
depends how you present.
Yeah. So, but I thought the way you presented it, so they do it. So
They do it a la pesky. They put a coupling. Look, let me put it this way. I wanted to say, maybe one has to be. I wanted to look. 4 pi is too much.
yeah, no. So they say
4 pi is too much. Let's do it.
So
Let's do it 3 or 4.
They do
Then
like
it's
this,
30.
right? They do like this, right? For instance, right?
Yeah.
Yeah. These are the kinds of things, right? And
But then they put this equal 4 pi.
yeah, and they say G squared is equal to 4. I thought
Yeah.
you were saying G squared is equal to 4 pi too.
Square.
You're saying G is 4 pi, or G squared is 4 pi.
Look, this G squared equal 4 pi is one of these things invented by Pascal.
No, I just want to make sure that I'm understanding what you're saying and mapping that on.
Which, by the way, numerically, I think it's even more correct than what I wrote.
So if I take this, what are you saying for G here?
16 pi squared.
You're saying this is
G4 pi. Yeah, G4 pi.
You're saying G is 4 pi.
Yes.
And they're saying G squared is 4 pi. Okay.
By the way, yeah, I mean, I think,
Still not totally
eh,
lining up.
because what are they saying?
They were saying, I mean, obviously it depends on the operator, right?
Okay. Sure, no, then there are various.
So, so here's,
These are some, but these are lab data, right?
This?
They're all lab. Yes, these are lab.
these are what,
Yeah, 10 TV, yeah, 10 TV, and then it's the same thing.
10 TeV.
Then you can put, then depends whether the coupling is 3 or 10, it becomes 30 or 100. Now, I grant to this use, this comes from the paper of Eichten, Lane, and Peskin. It's one of the first paper I read.
Yeah,
as a
I mean,
student,
at the end of the day,
1986, something like
At
this.
the end of the day, like we care about, in some sense, we care about this whole thing,
And
right?
numerically, I would say that, say, in QCD, the way they were putting this is based on some coupling they had in QCD. Now, in QCD, so strictly speaking, this coupling here, G star, okay, let's be fully honest, G star would have to be 4 pi divided by 10.
Right, yeah.
So, that's it. So if you say you have a theory with n equal 1, yeah, it's 4 pi. As soon as n is 3, 4, then it's becoming a fraction. So I put 4 pi equal 1. I put n equal 1. In that sense, I'm a crook. It's slightly less than that. Let's say it's 30.
But let me just think about this. So if they say it's 10, right?
No, that is silly.
No, but let's just hold up.
No,
They
because
say
then it's the coupling is like the standard model coupling.
No, but that's fine.
It's like n equal 100. Yeah.
Let's just I'm just trying to translate.
Yeah.
They say 10, and they
For
say
the-
10. G is square root of 4 pi, right?
No, the scale is 1. The
G-
10
no.
is with 1.
No, that's but G squared. I think they say it's 4 pi. I think they say it's 4 pi.
Really?
No.
No. Look, 200 GV.
It's hard for me to find this because PDG is always.
So the correction to the cross section goes like energy over cutoff square. Here
Yeah.
goes like energy over cutoff square. So 200 GV over 10 TeV, it's 10 to the minus 4, roughly. It's a bit more. It's a few in 10 to the minus 3. Lab has observed about 10,000 to
So-
100,000.
So this is PDG 2022, which is not what's in 2020, the other one. But this is what they say. They say if Lagrangian has this form, blah blah blah, with G squared 4 pi z equal to 1. We define this as that. And then they get these limits of like 8, 10.
Yes, you'll be all right. Sorry, let me just. Maybe.
I mean, it's a factor of 3 at the end of the day, right?
Yeah. Wait, one second. No, you're right. I think I screwed up. Look, it makes sense. Sorry. In fact, look at this. No, I screwed up. Yeah, then I screwed up. This is what is written. Great.
I mean, I always get confused. I always have to come back to this.
No,
because
you're right. Look, when I was writing these things, I think that's it. You see, now I'm putting my memory. This is the reason. Right?
This is 2022, but that should be.
No, it's correct. Okay, so EEE. So then it would be 30 TeV if you put 4 pi. That's actually
Now if I put in some.
because in the end, if you look at the numbers, okay, you have, let's say you have about 10,000, 10 to 100,000 events.
Mhm.
The statistical precision is 1%.
Mhm.
1% is that, yeah, if you put lambda with 1, Then you put the 4 pi, square root of 10, 3, because of that. So this was correct.
I mean,
Yeah,
The-
yeah,
the-
sorry, but it's funny because I took it for some notes I'd written some time ago, and I think I screwed up there. But what bothers me is that, the QQQ, let's go to see the QQQ. Yeah, the QQQ are much stronger.
yeah, you're much stronger, and I think that they're
Yeah,
even stronger than this now.
yeah, they're even stronger than this. Yeah, because this, I think I mixed up the one we had in our paper on flavor with the QQQ. I think. Let me go and check
Okay.
some slides that I
Okay.
presented where I had a fight with Michael. Let me just-
Okay. I'm just gonna run to the bathroom.
Let
While
me,
you
let
find
me
the
check
slides.
these slides. And, Automaticity, yes. So, Neil just pointed out that I'm full of shit. Let me show you. I am, but I was not. I became. So, oh shit. So, where is the, why am I not connected?
I didn't pause.
Oh, because I turned off the. Let me just do this.
Yeah, it says on the
Ah,
top.
yeah, it says recording. Yeah.
Yeah, let me show you this. Tim Johnston.
Also, shall we dim the light? Or?
Oh, it's gonna be quick. Don't worry. It's gonna be quick. Okay. So here it is. Maybe I should turn this off. Yeah, this is the thing, right? Oh, so yes, indeed, it's 30 TV with the 4 pi, not 100. No, I got recall. I got recall. Yeah, I screwed up. Yeah.
I never can remember, I always have to look it up.
No, I thought I remembered, and then I remember without the one, and then I added. But I wrote the notes yesterday, and then I was Anyway, however for the this is a talk of 2007, and you could see where we were with the quarks. Now we are. Are we now there?
Let's see.
We are even, I mean, we were probably at 50 for the quarks in this normalization.
Yeah, this
50,
says,
550.
50 TeV, yes. Yeah. So the argument that they made for the leptons is weaker, but now the quarks became so in the sense. Quark compositeness is very constrained. So anyway, let me drop this. Okay, maybe we'll discuss later. But thanks for pointing it out. I am full of shit. I screwed up this factor. Yeah, I remember the bound, and I remember that bound, but I remember that bound was without the 4 pi. Yeah, this is the thing. What should I do? Should I close it? Should I shut it off?
Because there are much stronger bound, the flavor is kind of.
Yeah, but there are more assumptions, right, that you have to add. Depends on what you assume for flavor.
But the flavor is not.
No, you have to assume. I mean, there it's. If you could have a composite scenario where the compositeness is flavor blind, right? No, it's less simple. Yeah, you have to start going around with assumptions. Yeah, to put bounds on flavor, you need to.
But let's say you assume MFV.
If you assume MFV, then then flavor is irrelevant. Then flavor constraints are very weak. If you assume MFV is called maximum.
Yeah, no, because for leptons it's irrelevant.
Yeah. Okay, so I think I have to speed up somehow. Okay, so as I said, in the case of Technicolor that I showed here, there was this difficulty where it seems like what you see and what you don't see comes at the same level. So in the more modern incarnation of the idea of Technicolor, which is known as conformal Technicolor, the idea is that this TT bar is some composite operator, which I indicate by H. sorry for the lack, or I can indicate by, yeah, let me indicate it by age. I no longer have the chart, this chart here is not very full. That's the last piece I have. I have H, which is an operator of dimension, dH, okay? A dimension dH does not have dimension, before in technical it has dimension 3, but now I can imagine a situation where the intermediate theory is a very non-trivial CFT. It's not a weakly, sorry, it's not a weakly coupled CFT, for which the corresponding operator could have dimension lower than 3, could have dimension 2.1, 1.6, okay? Now, in specific incarnations where that conformal theory is obtained with the gauge theory, then it's a lattice question what that value will be, okay? And on the lattice, it looks like this dimension cannot be made smaller than 2, okay? But in abstract CFTs, you may be able to do it. In fact, in CFTs that you can construct impunely, how are you? Impunely using ADS, CFT, using holography, you can basically do whatever you want. But then one can say, oh, but these are all CFTs that are in the swamplet. So, but in principle, you can consider lower dimensions, okay? And then this operator here will now scale like dH minus 1. And let's say here there are some ukavas, there's some ukavas, yij like that. Okay? So this is the modern version of technicolor. Okay? Now, of course, the ideal here is to what would you like here? You would like what would be the ideal in this situation? You would like this dA, because remember, this is what we see, okay? We would like, starting from a very high cutoff, what we see to go down in importance slower than that, okay? If you want, the running coupling here is E squared over lambda UV, okay? And when you get to the infrared scale, this is going to be of order, give you effects that are of order lambda IR over lambda UV squared. Here, the effective coupling goes down like E to the lambda UV to the DH minus 1. And in fact, if the Higgs were elementary of dimension 1, this would be essentially constant with energy. It's a marginal operator. On the other hand, if the H is bigger than 1, then it goes down. But you see, if the H is close to 1, this goes down slower than that. And its effects, when you reach the low energy scale, the scale where you cross to the standard model, they're only suppressed by the H minus 1. So all this to tell you that the fact that we observe these couplings, these are the Yukawa couplings, and we don't observe this, is clearly telling us two things, is pushing for two things, is pushing for lambda UV large, as large as possible. Of course, how large depends on what assumptions you make about the size of these couplings, okay? So that's, again, we enter into the realm of flavor assumptions. And let me just tell you that there is a range of assumptions from the most pessimistic to the most optimistic. The most optimistic, of course, the super optimistic is the one where there is no problem, everything is controlled by the Yukawa couplings. But if you want to go to a more generic theory of flavor, if you want to have a theory of flavor, you will not be able to realize that. And then you will have, for instance, the best thing you can realize here in the theory of flavor is that this goes like the square root of the product of the Yukawas. Okay? That's a typical result. But you can get worse than that, okay? So, but anyway, depending on the flavor hypothesis, there is a push to have lambda UV as large as possible. But when lambda UV becomes large, then unless D is very close to 1, the effects that you observe, the Yukawa coupling, go to 0. So at the same time, this implies the H as close as possible to 1. Okay? All right. On the other hand, on top of that, but you see, but when the H gets to 1, do you think we are still in business? You see, when the H goes to 1, H becomes a free field, okay? And there's a theorem that tells you that, there's a theorem that tells you that a field with this scaling relation, in other words, it's a field with dimension 1, it must be a free field, okay? If you want, that is because this correlator here satisfies the equation box of this equation here equals 0, okay? So it means that this field box satisfies the equation box H equals 0, and that's the equation of motion of a free scalar. Okay. So in the limit where H gets to dimension 1, H becomes a free field, and the property of the dimension of the products of H become additive, so that the dimension of H dagger H is now 2, and you get back the issue of the hierarchy stability. Okay? Because now you're writing things abstractly, but when the dimension of H goes to 1, you're getting back to the standard model. Okay, just getting back to the standard model. And then the question is, between Technicolor, where H has dimension 3, and the standard model, which has dimension 1, is there some sort of Frankenstein theory that can cut it across in a better way? Okay, and that was the question. Which to me seems like, in fact, it is a very obvious way to phrase the hierarchy tension in the standard model here. Okay, this is what you. So, as I said, in the standard model, it's beautiful. This is a marginal operator. This is irrelevant. This filters out what you don't see and preserves what you see. It's like gold mining. You have a very right mesh. You keep the gold, which is the Yukawas, what you see. You throw away the crap. Okay. But that implies that H has dimension 1, and you have a hierarchy issue.
And one of the Yukawa is really 1.
Eh?
I think it's important, top Yukawa is really 1, so that if Yukawas were smaller, it should
No. Sergei is saying, if we were dealing only with very small Yukawas like neutrino masses, then we can get away with higher dimensional operators. In fact, the neutrinos, in fact, the standard model, they successfully.
Not even the electron. Right?
No, but the bottom, even the bottom
right.
is not.
It's really important that top.
No, also the bottom is heavy.
Yeah.
I mean, it's not that much. Yeah, there is some space, but it's not that tiny. Yeah, the top is making it more dramatic. At the end here is the top that dominates. Okay, the constraint here, the constraint is dominated by the top. Okay, that's clear. Okay? Yes, the constraint is dominated by the top. In other words, yeah, there is a significantly big coupling, which is the top Yukawa, but also the bottom and the char are not that small. Okay, if you really want to separate the scale. Okay, if you really want to separate the scale. So, and the end point is where this has dimension 3, and okay, that you beautifully solve the hierarchy, Technicolor, but now what you see, what you don't see, and what you see are the same level. The question is that there is a middle ground, okay? And how do you phrase that? You see, the problem is that when what you would like to have is a situation like this, okay? Take, for instance, Technicolor. Technicolor is a situation where DH is 3. Okay, let's put here DH is equal to 1. This is, well, okay, let me put it 3 here. This is 1. This is 2. This is 1. Oh, sorry. Oh, this is 1. this is 2, and this is 3, okay? And this is 1.5, okay? And so this is dh, okay? This is dh. And you can think of exploring the space. Two parameters that characterize this theory are the dimension of this H composite operator and the dimension ds of the lowest dimension scalar singlet, okay, that you have in the system, okay, which is like the analog of H-Decker H, is the, which in Technicolor is the glue-glue kinetic term. This object here is a dimension of the most relevant deformation, which for Technicolor is essentially 4, and in the Higgs, in the standard model is 2. You would like this dimension to be not significantly smaller than 4. So in Technicolor, you are essentially here. Okay? The dimension of H is 3, the dimension of S is about 4. Okay? So the region where you want to be is sort of a region like here, okay, for the dimension of S. So you want the dimension of S. So in other words, let's assume the dimension of S hypothesis, dimension of S, is close to 4. Okay, then let's say you have a coupling C lambda UV 4 minus dimension of S, the operator S, the singlet S. Okay, and you know that the infrared scale lambda IR, we already derived it several times. We wrote it somewhere. I don't know whether we wrote it here. No, I canceled it. Okay. So the scale is the UV scale times this coefficient C 1 over 4 minus delta S. And remember, in the situation where this 4 minus delta S is a small number, maybe 0.1, even C equal 0.1, it gives you a significant hierarchy. Of course, that is becoming more difficult. The bigger lambda UV, but the bigger lambda UV, you need to get delta S closer to 1 to get the hierarchy, and or the further away delta S is from 4. So in other words, the large lambda UV is pushing delta S to 4, okay, keeping C fixed, not too small. Okay. So at the end of the day, if you take these three constraints together, okay, the first is pushing lambda large, but the fact that lambda is large is pushing the H to 1, and lambda large is pushing S to 4. Okay. So at the end, all these constraints are pushing you in this region here. Okay. A theory that matches all the requests to work has to have a dimension of H that is the dimension of H that is less than a bit above 4. This is 1.5, and the dimension of 4, a dimension of S which is close to 4. And it turns out that this region is essentially tangentially excluded by prime principle studies of the structure of conformality theories achieved with the bootstrap methodology. Okay, essentially, you find in a paper of Simons Duffin, Poland, and Vicky, there is a constraint like this in the models that are relevant. Okay, something like this, say like this, and you have to be below here. Okay, so essentially, this Frankenstein. And there are candidates for things here, but I think they require, that are even gauge theories, but I don't think these gauge theories have sufficient anomalous dimension to go down to here. There are some examples. In fact, Marcus is the author of one of the papers. We may discuss with him when he comes here. But that's
candidates from bootstrap studies or from?
No, from
in bootstrap there is no sign of any.
No, but you can argue, yeah. I mean, let's say differently. There is some fuzziness here, so there could be a match there, okay? And the question is whether there exists some simple theory that realizes that. There is a simple SU2 model, okay, which has a big anomalous dimension in principle, but is not big enough to go there. Okay, so that's essentially.
Sorry, I don't understand the reason for the exclusion. What paper does it come from?
Oh, this is a paper. This paper here is. You can check this paper. Okay,
I
no,
don't know
this
if
is
there's
not
like a
something that.
simple way to see it.
Oh,
or... No, okay.
No, okay, there are simple ways, but now, no, anyway, there are ways, okay? There are ways, but it's not entirely simple, no.
But I don't remember.
But what you understand is that, but you understand that this curve must exist by continuity, because you know when d goes to 1, you have to be here.
Yeah.
As I said, when dh is 1, the field is free, also this is 2, okay?
Yeah.
Then you have to be at 2. And then, if you make a reasonable hypothesis of continuity, there should be a
I
curve
see.
like that. And you could even compute a curve like that in using the Wilson epsilon expansion. Because then you can do a computation and you get something that has a resemblance that behaves in a slightly different way.
So I had a different question, but now that you mentioned this, so can you also tell that you have to be below the curve by a simple continuity argument, rather than above?
No, this is telling you that
I understand that there exists a curve now.
though the curve exists, it tells you that if there is an operator h of this dimensionality, there should be a singlet that has a dimension below here, that lives here. They must exist.
Yeah, my question is it simple to see that it's below rather than above? The curve divides two regions. Because of unitarity constraints. No?
That would be very weird if an arbitrarily small coupling allows you to have an arbitrarily large dimension for phi square. You see when I say it should work in the opposite direction.
Because
When the coupling, because you can view this as an anomalous dimension, right?
Yes.
So this effect should go to 0 with the coupling.
Yeah. So
And
now,
the distance from here is a measurement of the coupling.
yeah. So now the original question I had is
This question, Alberto, always leave you, takes always 15 seconds to answer. Okay, go ahead.
this instead is easy. What was missing in your original paper? Because you guys also had this square root curve.
Yeah, our original paper was more rough. We had less precision, and we were not imposing. These are models which have like SO4 symmetry. Here we are really imposing even the global symmetries. We are doing just a scalar. Okay?
Yeah,
Here
without
we're
any
really doing a multiplet. Okay? So this you could do with SO5 with precisely the models that are relevant for the concept construction.
But the basic idea of these new papers is the same.
Yeah, basically with a much better implementation of the algorithm.
And with the scalar, it's not as strong to say. But if you use the most improved version of your original bound.
This is the most improved version.
But that's assuming SO4 without assuming.
No, then they go down also without. It's even stronger. Even without the symmetry is stronger. Yeah, ours was somewhat rudimentary to start with, right? Okay. So this shows that, in reality, in fact, it's interesting. Okay, it shows how nice the standard model is in a sense, right? And how special, okay? And how difficult it is to go in a different direction. Nevertheless, there is a way out of this situation. And so how do we depict the situation here? The situation that we depict there is the one where it's called bilinear coupling, okay? It's the one where, let me indicate it pictorially. Is there a way to get some decent chalk? Not yellow chalks. White chalk, these are not. Yeah, let me use this one. And so the bilinear coupling I'm showing there is something like this, right? There is a quark, say a doublet, there's an up, and they mix to this composite edge. Okay. There is, however, another option to generate the Yukawa couplings, and this is the so-called partial compositeness mechanism. The idea is that the elementary fermions of the standard model, which I indicate by F is any Q, U, D, L, and E. Okay, any of the doublets, a singlet, let's call this L, this is the lepton doublet, where an elementary fermion mixes to a composite fermion. Okay, so the idea is that you have a situation like this, instead of having Q, U, H, this is a composite, divided by lambda to the BH minus 1. Now what you have is a mixing like standard model fermion. Okay, 2 more hours to go. Standard model fermions, okay, and let's put at the flavor, and there are some composite operators. You could think of this like baryons, okay? In the standard model, there are similar things made of 3 quarks. That is the field that interpolates for the proton, for instance. These are composite objects, okay? And they have some mixing, epsilon ij, or yeah, these are some mixing masses. And now these guys will have a dimension deep psi, okay? And by fixing the dimensions, the form will have to be, if this is dimension, if psi is dimension 3/2, like in elementary fermion, this will have to have a positive power of mass. Otherwise, it's something like 3. Four minus 3/2 minus deep psi, okay? It's 5/2 minus deep psi, okay? So in particular, if psi were to have dimension 5/2, this would be a marginal mixing. Because this is dimension 3/2. If this is dimension 5/2, this plus that is 4, and the coefficient is very much like an ordinary Yukawa. Okay? And now, the mathematical consistency of a conformal field theory through unitarity implies that deep psi is bigger or equal to 3/2. Okay, so any choice of dimension here bigger than 3/2 is acceptable. In particular, in the middle of this range, if you choose 5/2, you have a marginal mixing, which means that now you have a mixing between the standard model fermion and something that lives in the composite sector that is marginal, like the Yukawa couplings of the standard model. Okay, so now you have a situation where you separate stuff that eventually you may be able to see from the stuff that you don't see. The only problem is that this guy here is not precisely the standard model Yukawa, it's something else. It's a mixing between elementary fermions and composites, the composite operators. And this will only give rise to a mass, to a Yukawa coupling, in a situation where this composite, essentially, at some lower scale, this vertex here represents an interaction between composite resonances and the Higgs. And here there are the elementary fermion, for instance, left-handed fermion, and here a right-handed fermion. So at the scale where the gap develops, where was it? I erased it. Yeah, I erased it. No, yeah, I erased it. At the scale where the gap develops, the idea is that this object here will give rise to UCAV interactions. In fact, what will give rise, the UCAV interaction that gives rise here are easy to power count, okay? And let me view it this way. So what is this? This generates a mixing between ordinary fermions and the fermions, if you want. Let me tell you the story, okay? You don't need to understand the details of this counting, but generate a mixing between the states of the standard model and the states of this Higgs sector. Okay? These are supposed to be composite operators of the same sector, the same CFT sector that contains the Higgs. And this mixing is controlled by an operator of this dimensionality. So in a dimensionally, the strength of the mixing is given by its value at the UV scale, Ij here, times what? Times the energy over lambda UV to the deep psi minus 5 half. Okay? So this is like the running mixing. Okay? And that is again the usual story about if deep psi is very large, okay, this coupling is irrelevant. If deep psi is bigger than 5 half, and in fact this mixing goes down with energy. If instead it is dimension less than 5 half, if deep psi is very large, this mixing is irrelevant and goes down with energy. If deep psi is less than 5 half, this mixing grows with energy, okay? And you have both possibilities, okay? But it's interesting to be in the range where deep psi is around 5 half, okay? So that these things are marginal. And what comes out here is that at the low energy scale where you reach, I should write it somewhere. Maybe I should erase the stuff here. I had erased and now I had lost. Oh no, I still have it there, sorry. So, as I said, these couplings emerge at this scale, and they run, and then at this scale you match to the standard model, okay? So you have unknown physics, you have this intermediate regime where the standard model without Higgs is coupled to this generalized CFT, which eventually will give rise to the Higgs. You should view this as the mother QCD, which at the end gives rise to pions, okay? And they are coupled through gauge interactions and proto-Yukawa. Pictorially, you can really depict this coupling, as I said before. The proto-Yukawa is something like this, some fermion mixing to some composite operators. And this interaction here, and these are these epsilon ij, and the gauge is the elementary vector of elementary gauge fields of the standard model that couple to some current, to the corresponding electroweak or colored or hypercharged current from this sector. Very much like the photon in QCD couples to the electromagnetic current of quarks. Okay, it's exactly the same thing. Okay, and they're mixing like that. Okay, so what happens is that this mixing evolved with scale, and when you match to the low energy scale, let me tell you on very simple grounds, the numerical size of this mixing will be what? The original one, okay, between elementary fermion I and operator capital I, times the infrared scale, which is over the UV scale, over the UV scale, times deep psi minus 5 pi. Let me call this the effective mixing at the low scale, okay? So that means that at the low scale, the elementary fermion will have an amount of compositeness, is the amount by which is the strength of their mix, is numerical strength of their mixing with states of the Higgs sector. So this amount of compositeness controls the amount of the amount which the self-interaction of these guys, like this one here, okay, these are purely interaction of strong objects, how much this self-interaction between two composite fermions and the Higgs, how much it can be shared with the elementary ones, okay? So the basic rule to compute that, intuitive, okay? Of course you can formalize this, but the basic intuitive rule by which you can do this is that, okay? Is that you have let's say this is these are, so that there are composite operators H, psi, I, left, psi, J, right. Okay, these are operators of the CFT. Somehow they have a 3-point function, they're non-zero, so they're coupled in a sense. But when the CFT exits its scaling behavior, this operator will be able to interpolate for resonances. Okay, so very much like the proton field acting on the vacuum generates a proton. Okay, so essentially this will give rise to resonances, and one of the resonances is precisely the Higgs. And the coupling between these three resonances is controlled by some putative strong coupling of the strong sector, which will be normally it's 4 pi over root n, where n is the typical number of particles here. This is very rough, okay, but this is a strong coupling. It's certainly a coupling stronger, G star larger than any standard model coupling. Okay? And in this picture, then you have a mixing, which is given precisely by those epsilons here, further mixing between these composites and the elementary ones. Okay? So that means that the mixing, the coupling between the elementary fermions and the Higgs, which are the Yukawas, will be controlled by the mixing of the left and the mixing of the right. Okay? So the mixing of the left-handed fermion Ij bar, the effective mixing at the low scale, times the mixing of the right K, I don't know, L, okay? And there's gonna be some matrix J, L, some matrix C, J, L, which is expectedly order 1. These are just operators in the strong sector. If generically, you can assume that they're all interact. By the way, all these seemingly vague and squiggly things I'm doing here can be realized in a precise manner, are realized in a precise manner in the holographic realizations of this scenario based on more compactifications. Okay.
But presumably also that can be realized there. Also, presumably also the old picture, which is excluded by bootstrap.
Yeah. But that one is it's harder because the theory in ADS is a larger theory always, and then dimensions are additive. So the dimension of H dagger H is twice the dimension of H. Okay, so you need to go to the dimension of H that are 2 to be in business, and that is too large. You see what I'm saying, right? While here you have less constraint of having dimension 5.5. That's a big difference. Why do I want to tell you this? Okay. Let me imagine a situation, just for simplicity, where these are just delta ij. Okay, just imagine. It's not important, even if this CJL is an order 1 random matrix, it doesn't change anything. But imagine this one is a delta. So this object here, what is this? This is the Yukawa coupling. The Yukawa coupling is that the Yukawa coupling Ij is equal to some G star times the mixing matrix of the left fermions Ij times the mixing, in fact it's a star, but that's okay, of the right fermions K, this is Ik, times J. Okay, where I'm summing over, these are composite indices and these are elementary. Okay. So if you want, what is this? This is the sum of three vectors. So J is sum from 1 to 3. Let's assume that I have 3 of these composites, okay? And this is the sum of 3. So there's like, let's call, so there is epsilon bar I1. Let me call it epsilon 1. It's a vector. Epsilon I2, it's 2, and so on and so forth. So this is like G star times epsilon 1 plus epsilon 2 plus epsilon 3. These are like projectors, okay? And now, their normalization is controlled by this ratio. And now notice that by having tiny differences in the side by order 0.1, 0.2, let's say I have a family of 3 operators here to which I can mix. And they have one dimension 5½ the other has dimension 5½ plus 0.2, the other 5½ plus 0.4. They are distributed around that thing, okay, around this value. As soon as there is a hierarchy here, which we need to have, then these 3 epsilons, 1, 2, and 3, are hierarchically separated, okay? And epsilon 1, let's say, is smaller than epsilon 2, and epsilon 2 is smaller than epsilon 3, which means that you get a Yukawa matrix, which is essentially, imagine this is of order alpha square, epsilon 1 is of order alpha square, epsilon 2 is of order alpha, and epsilon 3 is of order 1. Then you get a Yukawa matrix that has the form alpha to the 4th, alpha 3, alpha square, alpha 1, 1, alpha 1, and then it's the same. Okay? So you get a situation where the ratio of quark masses of different neighborhood family goes like alpha square, and the mixing angle I plus 1 goes like alpha, which is very, very, very close to what we observe parametrically, okay? So all this to tell you that this construction is interesting because it gives you a theory of flavor, a theory which has the seed for explaining the broad variety, the hierarchy, and even the structure of mixing angles of the observed Yukawa coupling. So in a sense, we were forced to solve the Higgs issue, but we ended up being forced to solve or to address another question in standard model. Why do Yukawa coupling have such a structure? And this can address it. But like all theories,
so the heavy quarks will be more composite here, right? So
the more composite the quarks are, the more they share in the coupling, and the more, the bigger the Yukawa get. Essentially, you can view this as some very strongly coupled guy that shares the strong coupledness to the Higgs via this mixing to the lighter guys. And the more the lighter guys are mixed, and the more partially composite they are. In fact, this scenario is called partial compositeness, because these epsilons here measure, if you want, the amount of compositeness of ordinary flavors. Okay? Of course, the electron in this picture is very, very little composite. And okay. Okay. So this is very interesting. So this is just to illustrate how you can make good from some attempt to solve a bad. Like in all stories, there's always the bad side. And like in all stories where you really address the flavor problem, now you see the problem here is that the matrices that give rise to flavor now are not just the 3 matrices y up, y down, ye of the standard model. There are many more sources. You see, for every fermion type, for the Q, the U, the D, the L, for the 5 of them, there is a mixing matrix. Okay, there is a mixing matrix. So instead of 3 sources of flavor variation, 3 matrices, we have 5. So there's many more sources. The selection rules that in the standard model are so powerful because they're associated with just these 3 matrices. In this case, they're somewhat weaker. Okay, they're somewhat weaker, and therefore you predict unavoidably bigger flavor relating effects than the ones we see in the standard model, unless unless this scale lambda IR, which is the mass, which will be the mass of the new resonances, is going to be large. In other words, what happens here is that very much like you generate this, this is great, you say this is great, but you also, these composite fermions also have interactions like this. Is it clear what I mean? So this is a bit crappy the way, so is it clear what this is? This is a scattering of 4 composite fermions, right? Each endpoint here is one of these composite fermions, okay? Here I only have 2 composite fermions in the Higgs, here I have 4 of them, okay? So this is a 4 composite fermion scattering, but this, now I can put in here the epsilons. This generates a 4 F bar F, F bar F, I, J, K, L, a 4 fermion interaction among standard model fermions, okay? And this goes like the various epsilon I, epsilon J, epsilon K, epsilon L. Remember, the Yukawas go quadratically with the epsilons, so this goes like a Yukawa square, okay? So in particular, you generate unavoidably in this scenario, which per se, it's a beautiful scenario, I would say. What you generate interactions like this. One of the most relevant constraints is coming from the fact that you generate out of operators of this type, okay, which have 4 epsilons. If you generate an interaction of this type, it's y, something that goes like the down Yukawa times the strange Yukawa times some phase, which is arbitrary, times the mass of new physics, lambda IR square, and times d bar s. And this gives a contribution to kk bar, to delta kk bar.
Is it as bad?
And epsilon k.
Is it as bad as just original Technicolor?
No, this scale here, the constraint of what this is that lambda IR is bigger than 40. 30, depends how you view it, okay? So this is at the edge of what you can do. So that means that this is the mass of the resonances, okay? That means that this beautiful theory of flavor is at the edge, or maybe beyond the edge of discovery at FCC-HH. But it's a theory of flavor, okay? Of course, we will see in a moment this situation where you have this scale here. Well, normally in all my presentation, I use this scale, I call it M star. M star is the mass, just to indicate that this is going to be the mass of all the resonances. But this is the analog of lambda QC, right? It's the mass of the hadrons, okay? So which is way above the TV scale, where you would like to land.
And that's an improvement to Technicolor, because in Technicolor there is no light Higgs, and here you have both.
Yeah,
and that's what.
Right. Yes. Okay. So that means that this beautiful theory, if we want, because if you remember, at the end of the day, we will have m Higgs, delta m Higgs square, let me tell you, we will get something like y top square over 16 pi square, lambda IR square. And we already saw yesterday that this has to be below 1 TeV. So in the situation where we are here, there is a fine-tuning of 1 in at least 40 square, okay? This amount of cancellation, okay? So this is
And that's what
even more, even 1 in 100 square.
And that's what allows you to improve on the flavor problem, right? So it's at the expense of this fine-tuning.
So I'm not understanding.
No, I'm just trying to compare this.
Can we discuss that later? Sorry.
Yeah, sure.
No, because I'm not going to finish. Can I conclude on something? I will discuss that later, sorry. So what I want to say, if you want to lower the scale, by the way, you could have done this partial compositeness also in Technicolor. What buys you compare to Technicolor is simply the fact that you have a Higgs, which we have seen. That's the main thing, and you can control and you can tune. In Technicolor, you cannot tune. See, in Technicolor, there's no debate for what decides the scale, the mass scale of the Higgs. Now the Higgs is a Goldstone boson, there's a Goldstone manifold, and you can hope that some tuning lowers it a little bit, even further than what. So in a sense, having a Goldstone boson buys you the right to tune. Even a factor of 10, okay, that would be, in Technicolor you don't even have that. So Technicolor is too good as a theory. It's a very predictive theory, right? First approximation, it predicts the fermions are very, very light.
Okay, but that's exactly was my question. So you improve on flavor problem by tuning, but in Technicolor you don't have even that option to tune.
Yeah, exactly.
So here you have option to tune and using the
Exactly.
tuning.
So what I want to say, however, that if you want to have the scale lower, okay, now you have to start playing game. You start saying, oh no, these guys here are not general for 5 arbitrary matrices. But there's a limiting situation you can even think where these matrices are precisely controlled by the same amount of information that there is in the U-cavas of the standard model. In other words, you can invent some SU3 symmetry which is satisfied in this sector, and you can arrange things such that the total amount of sources, the total set of sources that break flavor are precisely the same quantum number under flavor as the U-cavas. This is the scenario minimum flavor violation. That's essentially, that allows you to bring the scale down to a few TV, not completely, okay? Because in this realization, this is not completely free because, for instance, you need to have universality, okay, in this thing, and it means that the up and the top, either the left or the right, should mix in the same way. And the compositeness of the up is tested at the LHC by the other side, and that is a very strong constraint. So even that requires a bit. But anyway, you can concoct a situation. This is what we discussed in our paper of the last spring, of last winter, where we did a systematic study of. We did it because it didn't exist in the literature. It's not that I had a particular fun in doing it. Okay? I wish somebody else had done it. Okay? But this was not done. And if you want to understand how the future progress in flavor physics collides and interacts with future progress in the expression of energy frontier and in precision measurement and in the Higgs coupling, you need to spell out hypotheses. And model building, as I said, is exploring this valley of tears of model space, okay? Anyway, there is a class of models where consistently and in a natural way, but somewhat ad hoc, not like in the standard model where those are the only sources, you set up a situation where self-consistently you have fewer sources, okay? And it's self-consistent because, because these are the only sources. They're consistent according to my rule of naturalness, right? You cannot generate the things that you don't have, okay? And in that case, you can bring the scale down to a few dB, say 4 or 5, okay? In some cases 3. But it's useless to go below 4 or 5 because already the bounds on the production of vectors is around 4.5 dB. This is the bound of 2 years ago. This is quite impressive. Anyway, so this is just to tell you that you can lower things. I just want to say one thing before going to lunch. There are several things I want to say, but what should I say? I have 5 minutes, so I think it's very hard to do better than this. You may ask yourself, how does the Higgs potential arise? Well, how does there are 2 rules here, 2 rules, okay? No, I think I have 1 minute, I don't know what to do. Whatever I do, I'm screwed. It's like checkmate, okay? I mean, I can go in a corner, then I have to exit the checkboard, okay, somewhere. So, what should I tell you? If you give me, I need to know, can you give me 5 to 10 minutes, or is too much? guys, you're dying, you're starving. 10 minutes? Okay,
I take 10 minutes that are, asymptotically approaching conclusions.
You have to end by telling us what the right explanation is.
It's unfortunate. Yeah, the problem of this course is that it doesn't, it's not that it doesn't end well, it doesn't end. If it didn't end well, okay, just some splatter blood, okay. It's never ending, but okay. I just to reassure, perhaps, those of you who think that this field is a bit vague and full of shit. For instance, remember the stuff I told you again about the computation of, you compute something like the pion mass from the top-down theory, you do the estimate from bottom-up, you get similar estimates. In the explicit construction of the scenario, and there are, and as I said, you can realize them either using work compactifications, in which case, it's interesting if you want, it's technically interesting, the computation of the exponential of the Higgs mass is free of ultraviolet divergences, so therefore it's insensitive to the UV, so it doesn't have, in other words, it behaves like in a situation where you don't have relevant deformations, in other words, that you don't see the destabilization of the separation of scales when you do quantum corrections. This is coming from the fact that in the x-dimensional construction, the Higgs arises as a Wilson line, okay, as a delocalized degree of freedom that is, in being delocalized, insensitive to quantum corrections at short distance. Okay? And this property of the x-dimensional theory maps to the fact that the original shifting did not have any relevant deformation. That's the way the things more or less map together. And if you take the example I showed there, I showed here of which I of course erased as usual because so there's an elementary so the idea is that let's say you have as I said, fermions acquire mass by mixing to the Higgs. Here is the fermion, and here it's a composite operator. Okay, this mixing here, very much like the gauge coupling, the electromagnetic gauge coupling in QCD, breaks the symmetry that protects the masslessness of the pion. Okay, here too, all these couplings that perturb the CFT, the gauge coupling, and the proto-Yukawa couplings, they break the symmetry that controls the Goldstone-ness of the Higgs. Okay, so in the limit in which these couplings are zero, the Higgs is exactly massless, and it's only their presence that gives rise to the Higgs potential. So in this scenario, in a sense, the Higgs potential is generated nicely by the standard model couplings. Okay, so you have a theory for the Higgs dynamics, and the way it works at leading order, you can draw it as a diagram like this. Okay, essentially you close a loop of elementary fermion, and if you want a vacuum loop where the two lines are the propagation of the composite operator and the propagation, say, of the standard model fermion. Okay, this is x, and this is in 0, this is in x, and this is in 0. Now, in the vacuum, this propagator, given that the Higgs is a Goldstone, will depend on the Higgs, okay, because the vacuum where you are expanding, and it would be depending in a way that can be eliminated if the couplings here were symmetric. But the coupling here breaks the symmetry, so the combination of the Higgs dependence of this propagator and the couplings here is such that this vacuum diagram depends on the Higgs and generates the potential. And you can quickly estimate what the potential is, okay? Because you see the mixing here, the epsilon, you have essentially epsilon, this could be epsilon left bar, okay? And remember the top Yukawa, which is the most relevant one, is G star times the mixing left and the mixing right. Now you see that this object here goes like the mixing the epsilon square, and now notice that if the two epsilons were the same, the result would and they both contributed, the result would go like y top over g star, okay? The potential, because like epsilon square is y top. Well, you know that in the standard model, the result is y top square. And this is just showing to you that the selection rule energy theory can always be made worse in the high energy theory. On the other hand, if one of these guys is 1, let's say this is 1, okay, and for some reason the mixing of the right-handed top does not break the symmetry, which is easy to realize, because it's a doublet, it's a singlet, then this is 1, and then epsilon left is y top over g star, okay, and then you compute this loop. This goes like epsilon left, it goes y top over g star square, and you start seeing your y top square here, and then you compute this loop here, and you find out that this result here goes like something like this. You're doing the integral, you're gonna get a 1/16 pi square from the loop. You get, in fact, you get also g star square from the overall loop. There's a y top over g star square, okay? And then you get the mass, the physical mass of the resonances, which is the infrared scale, okay? And then what you get the Higgs, okay? And then you get higher power of the nonlinearity from the strong sector, which are controlled by the scale of the strong sector and the coupling. For each leg of whenever you add a leg to an amplitude, you have to pay the dimension of the field and a coupling, okay? Remember, when you have the linear coupling in scalar theory, you have E. If you have the double thing, you have E square, and so on and so forth. If you emit another photon, you have E cube. So the number of legs is counted by the number of couplings. In this case, it's a strong coupling, and you go so on and so forth. You have G star to the fourth, H to the fourth, M star to the fourth, and so on. So this gives you a model for the Higgs potential, okay? And notice that this goes precisely like what you would expect. You have y top square over 16 pi square. The scale of new physics, this would be, in the low energy computation, this is the quadratic divergence, this is just the mass of the resonances times the Higgs. 1 plus nonlinearities, okay? Now, these nonlinearities are characterized by this quantity, G star over M star, okay, which is, you can call 1 over the decay constant of the theory. When you a mass divided by a coupling plays the role of EPFL, okay? This is the natural unit of measure of EPFL. This is like h squared over f squared, so on and so forth. So the natural expectation when you minimize this potential, never mind the signs, okay? Here this A plus B, and the value of A and B depend on the model, okay? And you can concoct models, classes of models where this A and B change in the range. You can even imagine a situation where at some specific model A, they're expected to be of order 1, but you can also concoct situation where A is too small, okay? And why is that, in a sense, important? It's important because that gives the model the possibility of having, because when you minimize the potential here, the expectation value of the Higgs, which is V, from there you have that V over F square is of order A over B, is equal to A over B, which is of order 1. But you could imagine a situation where A is a bit suppressed and this is smaller. This is important because this V and this V over, because of this V over F square controls is just the tuning. Okay? In an untuned situation, you would have the V over F is order 1. In other words, you get the right Higgs mass. Let's say M star is what it is, 1 or 2 TV, you get the right Higgs mass. But then this also predicts that V over F is of order 1. And as you see, this V over F here is what controls everywhere the Higgs nonlinearity is. So V over F controls Higgs nonlinearities. Okay, in particular, wherever you have like a Yukawa coupling like Q bar, H, T, or any other Fermi of the same B, then we'll give you the right Yukawa coupling if you've built it, the theory, but then you get unavoidably higher order effects from compositeness that are precisely measured by H over F. And when you look at the couplings of the Higgs, okay, to say BB bar, while this gives you precisely the resulting standard model, this gives you a deviation from it, which is precisely controlled by this one. So you have what I call normally sort of a Higgs theorem that tells you that the measurement of the Higgs couplings, and this is true in this scenario, it is also true in supersymmetry, that the measurement of Higgs couplings tests directly naturalness over naturalness. In other words, in a completely natural theory, okay, where I don't do any effort to do cancellations further than what the theory wants to do, then the level of nonlinearity from the Higgs sector must be of order 1. Okay? And this is, so there's no Q, this is 1. Okay? But in that situation, all the couplings of the standard model, or the Higgs to standard model particles, deviate order 1 from those of the standard model. In other words, this is just a very important thing to appreciate, that in a fully natural theory, like this one, the property of the Higgs deviate order 1 than the one from the standard model. In a sense, that is also the case in Technicolor. In Technicolor, they deviate order 1 because the Higgs is not even there. Okay, it's heavy. Okay, but this is also realized in basically all the situations in supersymmetry. Okay, you have to really concoct things to escape this. We can debate how plausible it is. And so this is just to tell you that measuring Higgs couplings is a very important and robust way to test what's going on in the Higgs sector. And now, of course, another way to do that is to look for resonances, okay? And in this case, there are two classes of resonances that are important to search. Okay, it's important to search, and these are the vectors and the fermions. Okay, the composite fermions and composite vectors. And basically, it works like this. The production of vectors is following the very same pattern of the production of the rho meson in E plus E minus annihilation. Remember, the production of the rho meson in E plus E minus, it goes like this. You have E plus E minus, they annihilate in a virtual photon. The virtual photon can go to QQ bar. Okay, so this is a current, this is a QCD current. Okay, the QQ bar bound to some crap and comes out a rho. Okay, so you can view it pictorially. You can view it like this. There's a photon exchange and there's a mixing with the rho meson. Okay, and the thing goes through. You have to exchange a photon, or you have two photon vertices, or you get an E square. Okay, but this is the annihilation is a 3-particle vertex. It cannot go like a coupling square. It should go like a single coupling. Because as I said, if you write in Lagrangian couplings to the front here, it's a long story. You can work with units of measure where couplings have dimension. That's another trick that I didn't have time to show you. So believe me, this has to go like a single power of the coupling. So what should I do to fix that? I only have one other coupling at hand, which is the coupling of the strong sector. So I get G star here. So the effective coupling of E plus E minus, which in the case of QCD, G star, is 4 pi over 3, which is the number of couplings. Okay? And that's roughly the right thing. Okay? And in fact, when you invert this and you square it, this you get 1 over G star squared, it goes like 3, okay? And it just measures the number of colors of the finite state. Okay. But anyway, the crucial thing is that the effective vertex of the plus, minus, and rho goes like that. So in this case, you have QQ bar at the LEC, you have a W, they are coupled to, and now this can mix through the fact that the electroweak symmetry is weakly gauged in the strong sector, and here you produce some resonance that you call W prime or Z prime. Okay. And the coupling here goes like precisely in, and you can view that in all the models, also in explicit models based on extra dimension, it goes like that. So notice that the stronger the strong sector, the weaker these guys couple to us. Okay? The stronger, the weaker they couple to us. They couple more to themselves, but in this particular case, they couple less. But anyway, and then how do you observe the decay? Well, these guys are strongly coupled, the Higgs is composite, and this decay into the longitudinal Goldstone boson, which is the particles in the Higgs sector, which is nothing but the longitudinal component of W and Z. So the process by which you look for the resonance is QQ bar going to W longitudinal, Z longitudinal, and Higgs, which are the 4 scalars, if you want, of the Higgs. Of course, maybe you haven't heard about there is this equivalence theorem that tells you that helicity 0 components of the vector bosons behave like scalars, like the scalars in the Higgs sector at energies much bigger than the W mass. Okay. And this is searched at the LHC, and it turns out that recent years have made a big progress. When we started LHC, the constraint on the mass of these guys, the mass of W prime and Z prime, was coming mostly indirectly from lab data, and was something like, it was coming from the fact that there is lab. There are corrections that are like MW over MW prime square to precision electroweak measurements, okay? Electroweak precision measurement. And at lab, we produce about 1 million to 10 million Z's, and statistically, that gives the statistical precision on measurement that is 1 over square root of 10 to 10 million, which is the order of the per mil. So lab tells you that this should be less than per mil, which was putting a bound on the mass of the W prime of 2.5, of 2-3 TeV, which is quite significant. It's significant because it was already telling us that if this mass is the universal mass of this composite sector, and it is the same as here, remember for naturalness from the top contribution, this should have been less than 500 GeV. So if this is already 2.5 TeV, it's 5 times bigger. This is already telling you that instead of being 0.5, you have 2.5 here. You need a cancellation with respect to what you get here of the order of a few %. So already at the beginning, if you believe that that is universal mass, this was already starting like that. But somehow you could argue, well, maybe this is the mass, there's some difference between fermions and vectors. This is what concerns the vectors. Maybe the fermions can be lighter, and then the mass there is the mass of fermions, so you don't have this tuning. It's debatable, okay? So that was already the situation, which is a few %. Tuning, 5 maybe. Now, 2022, there are studies, there's a particular study by Atlas and also by CMS, and the bound now on this particular case, MW prime, for the range where G star is about 3, which is the optimal range for the Higgs quartic. If you compute the Higgs quartic, if you look for the Higgs quartic, the M star disappears here. You just have the Higgs quartic is lambda is about y top square times G star square over 16 pi square. And to get the right quartic, G star is to be roughly between 2 and 4, okay? In that range, this bound is about 4.5. Okay. So already now, if this is a universal mass, this scenario is still on the level of 1%. Okay. So that's the situation, okay? And what is a bit disappointing to me is that if you buy this, okay, as I said, right now, so then you can ask yourself, what is now the goal, at least in this scenario, what do we gain, what do we learn more by measuring Higgs couplings in the next 15 years at high Lumi LHC? As I said, if that is the case, we already have a tuning of 1%. I also told you that Higgs couplings monitor the amount of fine tuning. Right now, we have checked that Higgs coupling, experiments tell us that Higgs coupling are always a standard model within 10%. Which is, okay, it's putting a model independent, I would say robust constraint on the amount of tuning you need, at least 10%. But somehow, these constraints are suggesting you that the actual situation is worse than that. Okay, you have perhaps probably 1%. Alas, high Lumi LHC will not do better than 1%. So at least in this scenario, I would say, at the stage where we are, high Lumi is not going to add much information. So I would try to go as quickly as possible to machine of higher energy. And I would also like to go to lunch. So I don't know whether I couldn't conclude, but I think this is eloquently telling you what's going on. So, thank you.
Thank you.
It's quite ridiculous. It's 11:30. It's 1:30. Now, Neil will now show that all the numbers I've given, they're all crap. Okay?
I did it offline.
No, that wasn't bad. Because I know these things. So I think this is a measure of standard deviation. Because I've known these things for so many years.
But you know, the thing is, very minor. That's the assumption that the only thing that the mixing are the stronger couple states. But if it's a theory where other like states kind of out, even if those states are not necessarily